Okay, welcome to another edition of Mr. Weis Solves an Old AP problem. This is 2014 problem number 5. It begins by giving us this region R that I've drawn on the board in purple that's bounded by three functions, well, three curves. The first is the black function y equals x e to the x squared, the blue function y equals negative 2x, and then the vertical line x equals 1. Part A of the problem asks us to compute the area of the region R. Find the area of R. This should be a straightforward integral problem. Let's see where it takes us. So the region R, the area of R is the integral from 0 to 1 of the top function minus the bottom function. So that's going to be x e to the x squared minus negative 2x dx. The first of these integrals, one of these integrals is pretty easy to do. I'll write it as 0, 1, x e to the x squared plus 2x dx. And I'm going to split this into two integrals. The integral from 0 to 1 of x e to the x squared dx plus 2 times the integral from 0 to 1 of x dx, using various rules of integrals. The second of these is pretty easy to do, so I'll just do that very quickly. But the first, a little bit harder, requires a U-Substitution, I believe. So for the first of these integrals, I'm going to let u equal x squared, so that du equals 2x dx. Looking at this integral then, I see that I have an x squared there and an x squared there. I have an x dx and I have an x dx. So things are going to work out beautifully, and this will become the integral. I'm going to have to change my limits of integration. I'll do that in a second. Because x dx equals half of du, I'm going to have a 1/2 on the outside, e to the u du. For my limits of integration, I'm just plugging in 0 and 1 for x squared. When I plug in 0, I get 0, and when I plug in 1, I get 1. Interesting that they didn't change. And then the second integral was easy to do. We'll do it right now. So this is 2 times 1/2 x squared from 1 down to 0. This ends up equaling 1/2. The antiderivative of e to the u is e to the u from 1 down to 0 plus, and when I plug in here, I just end up getting 1. This becomes then 1/2 e minus 1/2 e to the 0, which is 1, plus 1. So altogether, I think we find out that the answer is e minus 1 over 2. Okay, part B is a little bit harder, though they don't actually ask you to compute the integral, so in that sense it's actually kind of easier. All they ask is that you set up an integral so that you would be able to compute the volume of the solid generated by this region if we were to rotate it about the line y equals negative 2. So y equals negative 2 is right here. And we are going to take this function, this region, and we're going to rotate around that line. So whenever I do a volume of rotation, I like to use the method of representative rectangles. So I'm rotating around this axis here. I'm going to grab a random point along this axis. This is going to be an x point. And I'm going to try to figure out what happens to that as it gets rotated around this region. So, if I do that, I have this beautiful little representative rectangle here, which would be something like this. It gets rotated about this. So like down here is going to come like so. And this part is going to go all the way down like that. And we get that shape that looks something like this. If I were to finish it all the way around, I see that I'm getting some kind of a washer shape. And we want to find the volume of that washer. So the way this ends up working then is we need to find So we're going to have to do, there are two radiuses to consider here. There is the smaller radius, which would be this distance right here, which is little r. And then there's this larger radius, which is capital R. Let's get rid of this so we don't get confused by R being that region. So we've got the larger radius and the smaller radius. And we know that basically the volume we're trying to calculate is going to be the integral as x goes from 0 to 1 of pi times the bigger radius squared minus pi times the little radius squared dx. The question simply comes, what are these big and little radii? And they should depend on x, as you can see right here. So let's try to figure it out. So for little r is this distance right here. At this x value that I've picked, the y value right here is negative 2x, and this is down at negative 2, so little r ends up equaling negative 2x minus negative 2, which comes out to be 2 minus 2x if I do a little bit of work. Big R, on the other hand, is going to be, at this x value, at this x value right here, this height is x e to the x squared. I need to add to that another 2, a distance of 2 right here, and I'll get the whole radius r. So in this case, you could also subtract it. It's the same that I did from before. I'll in fact do it that way. So it's going to be x e to the x squared minus negative 2. Note that that actually ends up being x e to the x squared, this distance, plus 2, that distance. That's your capital R. So we throw these up into the volume formula, volume integral from 0 to 1. Pull out the pi if I want. Capital R is x e to the x squared plus 2 squared minus little r 2 minus 2x squared dx. And that's the answer to that problem. Okay, the last problem also would generally be a hard problem if you had to compute it all the way, but they're being nice and they're just asking you to set some stuff up and leave the answer with your setup. So in this case, what they wanted us to do is write down, but do not evaluate, an expression involving one or more integrals that gives the perimeter of the region R that we've been talking about in this problem. So we want the perimeter. Well, a good thing for us is that our perimeter is made up of these 3 little curves. I've got colors for each one, so I can take advantage of the fact that I've got these colors, and we can try to write down what the perimeter will be. I'm going to use as few integrals as I possibly can. So I think I can do this with just one integral. So let's start with the easiest of the distances. The perimeter consists of 3 segments. Let's do the red segment first. So the red segment is actually really easy. Given that it is just a vertical line, this point right here is 1 comma 1 e to the 1 squared. And this point down here is 1 comma negative 2. So this distance is just the difference in these y values. So 1 e to the 1 squared is otherwise known as e, minus negative 2, or e plus 2. And that's the red business. The blue business is also fairly easy to do, because there's a nice triangle that I can use here. Picture clearly, by the way, not drawn to scale, because this length is supposedly 1, but the red length right here is supposedly 2. So the blue length I can find just by using Pythagoras' theorem. The blue length is equal to the square root of 1 squared plus 2 squared, otherwise known as root 5. The part that requires any work at all really is the black length. This is a curvy object, and so finding its length requires us to find essentially the arc length. Hopefully you remember how one computes the arc length of a function over a region. In general, arc length equals, arc length is the integral from a to b of the square root of 1 plus f prime of x squared dx. It's this that I'll be using. It's the arc length as the x ranges from a to b, and there are some requirements for this to be true, but in general, this is what the arc length equals. So in our case, x is only going from 0 to 1, so it's the integral from 0 to 1 of the square root of 1 plus, oh boy, we have to find the derivative of this thing and square it. So let's do that. I'd like to try to find, let's call this f of x, so that I know what I'm talking about, and I'm going to find f prime. This is going to require a product rule and a chain rule. So here we go, product rule first. We've got x times e to the x squared. The derivative of that is, take the derivative of the first, 1. Leave the second alone. Plus, leave the first alone, take the derivative of the second. I'm now trying to take the derivative of e to the x squared. This requires a chain rule. The derivative of e to the is e to the. Leave the inside alone. Whenever I say leave the inside alone, I like to underline it because the chain rule then reminds me that after that I have to take the derivative of whatever it was that I left alone. For me, it's anything that's underlined. So I take the derivative of x squared, which is 2x. I can clean this up a little bit. This is basically e to the x squared times 1 plus 2x squared. And I'm plugging that into our formula for the arc length, and it becomes all of that stuff squared. So e to the x squared times 1 plus 2x squared squared dx. My final answer to this problem then is to add up the red, the blue, and the black. Don't forget to add all three of those things up. So I'm just going to go like this, and there you have it.